Welcome to this deep dive into direct current electrical measurements. In this session, we will not only learn how to measure quantities like voltage, current, and resistance in DC circuits, we will explore the physical meaning and origins behind those measurements. Let's build intuition from the ground up. Let's begin by understanding what direct current or DC really is. From a microscopic physical perspective, DC represents the steady unidirectional flow of electric charge, typically electrons in a conductor. In metals, electrons are the mobile carriers. A DC voltage source, such as a battery, creates an electric field that pushes these electrons in one direction continuously. This steady flow makes DC ideal for precise electrical measurements, especially in laboratory settings. Voltage is the electric potential difference between 2 points. You can think of it as the pressure that pushes electrons through a conductor. From a field theory perspective, voltage is the line integral of the electric field between 2 points. The voltage is equal to the minus integral of the EDL. For example, when measuring the voltage across a resistor, you're effectively probing how much work per unit charge the electric field does to move electrons from one terminal to the other. Current is the rate at which charge flows through a cross-section of a conductor. Microscopically, it is related to drift velocity of electrons, charge density, and the conductor's cross-sectional area. Mathematically, I is equal to N times Q times A times V of D, where N is the electron density, Q the charge, A the area, and V of D the drift velocity. For example, measuring current with an ammeter involves breaking the circuit and inserting the meter in series because you want to count how much charge flows through it. Resistance arises due to scattering of electrons in a conductor by lattice vibrations, impurities, and defects. It's fundamentally related to how easily charge can move through the material. The resistance of a specific medium can be calculated as R equal to rho times L over A, where rho is the resistivity of the material, which is also the 1 over conductivity of the material. L is the length of the medium, and A is its surface. Ohm's law links all the voltage, current, and resistance, telling us that the voltage across any medium is equal to amount of current passing through it times its resistance. A voltmeter measures potential difference between 2 points. To avoid disturbing the circuit, it should draw minimal current. This is why voltmeters are designed with very high internal resistance, typically in the mega-ohm range. The voltmeter should be connected in parallel with the component of interest. An ammeter measures current. To ensure all the current flows through it, it must have very low internal resistance, ideally close to zero. The ammeter should be connected in series with the circuit branch. An ohmmeter usually works by injecting a small current through a resistor and measuring the resulting voltage to calculate resistance based on Ohm's law. You should always disconnect a component from any live circuit before measuring resistance to avoid damaging the meter or getting false readings. For example, let's measure the voltage across a battery. We should set the multimeter to DC volts. Then place the black probe on the negative terminal, red on the positive. The reading will be, for example, around 1.5 V if the battery is healthy. Let's go through another for measuring current in an LED circuit. First, we should break the loop and insert the ammeter in series with the LED and resistor. Make sure the current is under the safe range for both the LED and meter. In such a case, the typical reading may be around 1020 mA. What if we want to measure the resistance? First, we have to disconnect the resistor from any power source. Then set our meter to ohms. Now we have to connect touch probes across the resistor terminals. The value should match the color code, say 220 ohm. In any DC measurement, uncertainty and error are always present. Random errors come from noise and contact quality. Systematic errors arise from calibration drift or poor probe connection. Resolution limitations come from how many digits your meter displays. We quantify total uncertainty as U combined equal to square root of square of type A uncertainty plus square of type B uncertainty. You can find the details about the concept of uncertainty, the type A, type B, and their estimation methods in another video posted in my channel. Let's review some important tips for accurate DC measurements. We have to always use proper probe placement. We need to wait a few seconds for readings to settle. Be aware of loading effects. Your meter might influence the circuit. Use averaging if the meter supports it. And always zero your instrument if possible. DC measurement is the foundation of everything from battery-powered circuits to microcontroller projects. Understanding not just how to measure, but why these quantities behave the way they do, transforms you from a technician into an engineer. Thanks for watching, and let's keep building intuition and rigor together.